So I'm Andrew Chen. I'm the panel organizer. What we're going to do is talk today about sustainability challenges for HPC. The context is, of course, as I'm sure you're all aware, that there's aggressive government goals to decarbonize their economies and reduce negative environmental impacts broadly. And computing is sort of in a special place in this. Computing and HPC together have challenges around sustainability because of their rapidly proliferating use and very, very fast technology life cycles. So we're going to spend some time talking today about growing power consumption, which you might think of as Scope 2, increasing Scope 3 and e-waste kinds of challenges, sometimes called embedded carbon and environmental pollution, and really trying to get at some of the challenges that we face as a community to reduce and hopefully eventually eliminate our carbon footprint, our e-waste footprint, and other things, given the ambitious goals that much of the community is pushing. As participants, we were asked to write down WIFM, right? What's in it for you, really, for the participants here. What we advertised to the SC committee was that we would characterize a number of these growing challenges, describe emerging solutions, and try and create an increased awareness of the challenges for sustainability that HPC faces, and share with you some tangible ideas for solutions that your organizations or the community could pursue more broadly. So that's the context for the panel. I'm going to give a brief intro and air a couple of ideas, and then I'll give it over to the panelists. So I've introduced myself, but I'll introduce at a little more length our panelists right before they speak. But we have Steve Hammond from NREL, Bill Magro from Google, Michael Mcnamara from Lancium, and Eric Riddell from IT Renew. Thank you all for participating. It's actually particularly timely that we have this panel on sustainability because COP26 has been going on and maybe just completed. I don't know if they're still holding them up there to negotiate. But entire economies, including, of course, HPC and computing, have made the commitment to get to net zero by various times, whether it's 2050, 2060, or 2070, right? We now have commitments from all these nations. But it's all in the context of this large gap, right? And this chart was made before COP26, so I imagine the situation's better now. But the orange kind of wide band is the projection with current policies, and the blue band is the projection needed in order to get to 1.5 degrees C or 2.7 degrees Fahrenheit. If you look at the charts for different regions of the world and their current sort of emissions, you can see that actually none of us is really on a trajectory that is compatible with that blue line on the left graph. So really, this is the challenge that we're all facing, at least in the Scope 2 carbon emissions from power space. So what does this all have to do with HPC? Data centers in particular is how we mostly think about it. So Bobby Mann, who was then at Microsoft, gave a really nice talk at Micro last year and made this very nice chart, which I borrowed, that talks about various kinds of carbon impact that we have when we build large-scale computing systems. So there is, of course, a large amount of energy around use. Let me see. And that's normally what we think about, Scope 2 emissions, where you have energy being consumed, usually in the form of electricity, right, to operate the computing equipment and networking. But there's also a very, very significant amount of energy that corresponds to the production, right, of both the data center facilities as well as the computing electronics and the like. And that's often referred to as Scope 3 or embodied carbon. Fortunately, in computing, we tend to not have a lot of downstream Scope 3 carbon, so we'll focus on Scope 3 here. And then, of course, we have kind of the challenging practice of a fast-moving technology, which is that we dispose of our systems after a relatively short lifetime. So e-waste is one of the significant challenges associated with that. We're producing large quantities of e-waste. So how big is this? Well, it's kind of hard to get your arms around this, but if you use the top 500 as a proxy, we recently estimated the total power of the top 500 computer systems as something like 600 megawatts, at least nominally, over a 24-hour by 365-day period. That would produce something like 5 terawatt hours of consumption, with the top 10 accounting for a very significant slice of that, over 100 megawatts. If you were to calculate how much carbon that is at the US average for carbon emissions per kilowatt hour of power, you would come to a number that's something like 2 million metric tons of CO2 per year, or the equivalent output of something like 285,000 households. So significant. Of course, the top 500 is not all of HPC. So if it were perhaps 20% of HPC, you can pick your own estimate here. Perhaps you're talking about a substantial multiple larger than that. And I think we're all aware that there's generally a trend of increasing both power density and power in all kinds of computing systems, and HPC is certainly no exception. So one of the challenges that we'll talk about today is how can HPC reduce its Scope 2 carbon emissions? And obvious approaches include things like efficiency, offset, and more. And I'm going to talk about one idea that my group has been exploring, synergy with the renewable grid, just to sort of open up the space of talking about different ideas. So one of the things we observed is that it's not a very easy thing to just wait for the power grid to become net zero. For a couple of reasons. One is the power grid has a hard time getting to net zero. It's extremely difficult to get to a fully renewable grid. The second reason that computing shouldn't just wait for the power grid to come to net zero is that computing loads are a large and growing part of the power grid load. And if you introduce a computing load as a constant load, like data centers are typically pretty close to, it actually retards the ability of the grid to become carbon free. So we've done some studies in that space, but I'll just put it out there as a technical fact that if you don't modulate your load in some way that's harmonious with the grid, you're actually making it harder to decarbonize the grid. So we've been exploring a project called Zero Carbon Cloud, which explores this idea that instead of having all of your data centers as constant loads in the grid, that we might be able to have computing equipment modulate its consumption to the availability of excess renewable power. So the conceptual idea is kind of like you put some of your computing equipment on the unreliable side of the grid, and you use excess renewable energy when it's available. And it turns out if you take this study to its logical conclusion, and we've been working at this for a while, and you look at scientific kinds of computing workloads, you can actually find some amazing opportunities. So we did a study that looked at Argon's workloads for about a year. We compared things like performance as measured by turnaround time, throughput, and measured that against total cost of ownership. And we imagined a system in which you had one reliably powered system and one powered by this intermittently available, but mostly available, renewable energy. And this system effectively eliminates 50% of the carbon emissions footprint for this aggregate computing system. And it turns out, if you work through the details of what you might be able to build in terms of a cheaper facility, that you can actually discover that this approach, a holistic approach that looks at TCO from capital equipment on through operational cost and power and so on, could lead you to the conclusion that you could build a system with higher throughput per $1 million of TCO per year, and something this community cares a lot about, higher peak performance per $1 million of TCO per year. The numbers were 45% higher and 80% higher. So this is in addition to the 50% emissions reduction. So the point isn't so much the details of the study. The point is to point out that if you look at this in the right way, that there may be opportunities that not only reduce the carbon emissions footprint, but also create new opportunities for new capability and even cost effectiveness. And I think we're going to hear about some of those kinds of ideas. The other area that's obviously a big challenge for HPC and computing in general is Scope 3 and e-waste. And what is Scope 3? Well, it typically includes the building, the use, decommissioning, right, of all of those kinds of things, from the concrete in the ground underneath the data center, on through the structures, on through all the computing equipment. And typically, people are taking that as a capital investment and then annualizing, right, this Scope 3 or embedded carbon or e-waste over the lifetime of the facility and the equipment. A lot of the Scope 3 in these data centers can come from the electronic components, because they're energy intensive in their manufacture, and they also are typically operated with a relatively short lifetime, perhaps 3 years, perhaps 5 years. For example, there was a recently published study that suggested that the embodied carbon or embedded carbon or scope 3 carbon for the equipment and the facilities could be, by Facebook's estimate, 23 times greater than the scope 2 emissions. And Facebook estimated for Google, we won't characterize it as Google's position on this, perhaps 20 times greater than the scope 2 emissions. And really what's going on here is kind of interesting. Because they're arguing that they purchased offsets to reduce their scope 2 carbon, these ratios can be very, very large because they're shrinking one side with the purchasing of those offsets. So I think those numbers are perhaps not that large a ratio, but they're very significant. Embodied carbon is a very significant issue. And it turns out that scope 3 depends on who you buy hardware from, what process or feature sizes it uses, and how long you operate it. All things that HPC tends to push the extreme envelope of. And there can be large differences. For example, in that paper that was published in HPCA that I cited, they actually point out that embodied carbon for 2 different manufacturing companies, TSMC and Intel, could vary by as much as 2.5 times, right, for the embodied carbon in a particular class of products. So the challenge here is, what can HPC do to reduce its scope 3 and e-waste annualized impact? Buy less, improve suppliers, extend lifetime, reuse, recycle. We'll hear about some of those ideas. And just to, again, try to open up the thinking a little bit, there are win-win kinds of scenarios here. So one scenario that we've been looking at is looking at if we change the practice of a hypothetical HPC outfit, such as funded by the NSF's Office for Advanced Cyber Infrastructure, that it's not unusual for systems to be put up and run for 5 years and then disposed because of limited space or power limits, right, at the university or at the facility that it's deployed. Then you would go on to buy new hardware. An alternative, actually, that has emerged is to deploy that hardware instead at a secondary facility where you have low-cost green energy available on site. And those approaches could be used to extend the lifetime of the equipment, say, by another 3 years, so you get a longer lifetime. And it turns out that that's a win-win-win, because you not only can reduce the e-waste impact by nearly 60%, but you can get 36 to 90% higher cost efficiency than buying new equipment. And that works very, very well for this HPC kind of capacity-oriented community. So that's another example where if you look at the right scope, you may actually be able to find win things that are not a cost, but in fact a net win for your organization. So with that, I'm going to read the panel charge questions and then pass to my panelists here. How do you see these challenges? What are the most critical? What are our responsibilities? What are best practices? How do we overcome the economic challenges? What are some of the new opportunities to change the game? And, can we get there? So with that, let me introduce first Steve Hammond, who's on the Zoom. Steve, you want to go ahead and open your camera? And I'm going to stop sharing and give it over to you. Steve has long been one of the champions for renewable and sustainable data centers at the National Renewable Energy Lab, where he has been operating a system he's going to tell you about, I think. And he's the senior research advisor for a whole portfolio of programs in this energy efficient computing area. Steve?
Yeah, thanks, Andrew. I'm trying to share my screen and take
let me stop sharing here to get out of your way here, perhaps. Did you get it?
Looks like it worked. Okay, does that work?
Yeah. Go ahead.
Okay, thanks, Andrew. Yeah, as Andrew said, I've been at NREL for just over 20 years, and most of that time I led the lab's computational science research efforts, including operating the world's most energy efficient data center. So what I'd like to say a bit about first is what's been done, a bit about what's been proven effective for data center sustainability, and then conclude with some thoughts about the future. Let me see if I can get this to go. Oh, great. So we took a holistic approach to sustainability. Something to keep in mind is the choices you make, and some of the things that Andrew called out, the choices you make regarding packaging, power, cooling, energy recovery, all of these determine your energy consumption, the sustainability, and of course, they drive your total cost of ownership. A couple of tenets that we held in this as we were looking at our efforts was first to focus on efficiency. So minimize in the broadest sense, the resources that you need. From there, that takes a number of different forms. Get the most effective computing for your particular domain. I don't want to presume what what sorts of compute is best for the problems you're trying to solve, but something along, get the most bang for your buck, right? Ops per watt, whatever your favorite metric. As we all know, computers, generate a lot of heat as a byproduct, so make sure you cool that efficiently, get your heat exchange closest to where the heat is being generated. In our case, we did warm water liquid cooling, we did direct component cooling, and sort of pioneered this about a decade ago. And then also capture and reuse the waste heat. So, we want the bytes and the BTUs. The second aspect to sustainability is to utilize, then once you've minimized what you need, get what you need from the most sustainable ways possible. It's clear these sorts of things are, provide a solid approach, but it's also clear that no one approach fits every solution, wherever you are. So what works here for us in Colorado may be different than what works in the southeastern US or warmer climates or hotter climates, but the the fundamentals of the physics don't change in terms of heat exchange and power. So, you might have different ways of cooling. You may have an opportunity, drawing on a body of water, and that's not too far away for doing heat exchange that way. But one of the things we learned was often the energy efficient solutions are also cost-effective solutions. So we didn't have to spend a lot of money to save on the energy efficiency side. So that was something that was actually a little bit surprising. We thought there might be a premium. I want to share a little bit about what we've done at NREL. We adopted a chips to bricks approach rather than having an isolated data center. We integrated our data center into a larger research facility shown in the middle here. And then that was integrated into the campus. And that sort of higher level of integration gave us many more opportunities for efficiency. So we built a LEED Platinum facility, including the data center. We focused on highly efficient evaporative cooling. It's one of those instances where evaporative cooling costs less and uses less energy. So we have no mechanical cooling, inexpensive, or inefficient chillers or power hungry, compressors. We work directly with physics. It's clear liquids are about 3 orders of magnitude more effective for cooling than air. So we use direct component level liquid cooling. Our cooling supply is 25C. All the vendors are aware of what it takes to sort of have a system in our data center. But then we also wanted to use the waste heat. So we asked the vendors to return, at least 35 to 40 C return water that was captured and used in our offices and lab space. We used it for snow melt, and we used it on campus in shoulder months. So we, delayed the use of boilers for taking the chill off the morning. So one of the things we did was when we were designing office space in the nearby buildings was we use active chilled beams, which are very effective means of using sort of low-grade waste heat for office and lab space cooling. So you start to think outside the box, outside of just computing, and think about the ecosystem within which it resides. Another thing that we realized pretty early on was not only is our data center the single largest power consumer on campus, it was also the single largest water consumer on campus. Because I said we made the choice to go to evaporative cooling. We were using about 2 million gallons per megawatt year of water. About 6 years ago, we had a project in collaboration with Sandia National Laboratories and Johnson Controls, and we installed a prototype thermosiphon dry cooler. We wanted to do a compare and contrast of that to see how effective it was at producing the cooling water that we needed without sacrificing the efficiency. Happy to report this was a early industry partnership. This was a prototype unit, pre-production. We installed it, and in 5 years of operation, we saved 6.5 million gallons of water. I don't remember how many Olympic-sized swimming pools that is, but it was quite a lot of water. So it was nice to know there are solutions out there that you can use. So depending on where you are, and depending on your water concerns, pay attention to water. It's not just there's all sorts of other sort of natural resources that we need to conserve. Another of our things that we worked with was looking at hydrogen as a source of energy in our data center. So the premise was, what if hydrogen was as common as natural gas is right now? And so we have, because of other research efforts we have, we generate our own green hydrogen on campus. So we use renewable energy and electrolyzers to produce hydrogen from our hydrogen storage yard that happens to be on the back of our research building. We plumbed hydrogen into our data center in a pipe with a diameter about the size of your pinky. We can carry the equivalent, the energy equivalent of a megawatt of energy from hydrogen. And from the fuel cells, this is a converted automotive fuel cell from Daimler that produces 380 volt DC. We provided short runs of DC directly to 2 racks of compute. We demonstrated load following capabilities of fuel cell. It's extremely responsive. So this is a PEM fuel cell. Another thing that we were able to do is we captured 65-degree waste heat, or 65C waste heat from the fuel cell in a sort of combined heat and power approach. And again, because we capture the waste heat, we were able to use that in our waste heat capture reuse. Things we thought of was, again, short runs of DC to rethink a data center if hydrogen was available. You could do N+1 fuel cell redundancy, so do rack level redundancy within your rows from a reliability. Now you can eliminate UPS, you can eliminate backup generators because you're doing row level redundancy, and that was a great experiment. We ran that over the course of about 24 months. Byproduct of that is some waste heat that we captured and a bit of water vapor that goes through that mast that you have. Learned a lot about safety. Nobody wanted to have our data center be the next sort of Hindenburg, so we paid very careful attention to sort of how to do this safely. So that was an important aspect. Again, our partners there were Daimler, HPE, and Power Electronics through Power Innovations. So in terms of thinking outside the box, if hydrogen was available, that would be a very interesting solution. Saves a lot of copper, actually. And lastly, a few thoughts about the future. I confess I have more sort of ideas about what the problems are than ready solutions. But it's clear that computing is a high energy intensity enterprise. Our everyday reliance on it continues to grow. HPC is just a fraction of the market. If you think about the broader sort of enterprise level data centers and hyper centers, HPC is just a small portion, but we can lead by example. Some of the dramatic cost reductions in the costs of clean energy is going to help, but as Andrew noted, that's going to take a long time to transition to, rather than just waiting for cleaning up the grids. Our current model of 4-year life cycle with forklift upgrades needs to be rethought. How can we extend the life? What can we reuse? And again, thinking sort of broader, holistically, I think we need better cradle to grave analysis of the packaging, the plastics, how we reclaim precious metals. It sort of boggles my mind how much we just have to throw away when we get a new system in. And I know it's driven by availability of spares, and can we get replacement parts anymore, and embrittlement of cabling and all, but this age-old triangle of reduce, reuse, and recycle is still applicable, and we ought to think about it in the broader context of HPC, seeing as sustainability. And with that, I'll yield my time on the floor and look forward to the open discussion.
Thanks very much, Steve. I always find that hydrogen fuel cell data center project just remarkable. Let's see if I can get the right presentation up here. Our next speaker, is that the right presentation?
Yeah, that's it.
Yeah. Our next speaker is Bill Magro, who, as he was just telling me, is no stranger to this community. He told me this is his 20th?
29th.
29th, oh my gosh, 29th SC. Obviously, many of us knew him for his very long stint at Intel as a leader in HPC, but he is currently the chief technologist for HPC at Google. Bill.
Is it okay if I stand up?
By all means.
Thanks, Andrew. Hi, everybody. So I just wanted to talk a little bit about what Google is trying to do in terms of our commitment to sustainability and show you some data points. As Andrew said, this is a really hard problem. There's no easy solutions like for the grid, but we're trying to do some concrete things that help drive the grid towards net zero. So let's just get into it. The first thing that we're doing at Google Cloud is trying to operate the cleanest cloud in the industry. So one part, of course, is just using less energy. And an advantage of building massive data centers and driving utilization up by bringing lots of customers together onto a common cloud is that you can actually achieve more efficiency from an energy perspective. We can also invest in the technologies like water cooling and building rainwater collection pods to cool our data centers and custom hardware to really drive our PUEs down. So, compared to the average data center, we're about twice as efficient today. And then in terms of adopting new technologies, we're rapidly adopting the latest technologies, and we're also innovating with things like our TPUs for machine learning, which can do machine learning, which is a very big consumer of data center flops, of course, and do it with lower energy. So that's one way you can reduce the footprint. So just as an example, our data point, we're 7 times more compute delivered per watt versus just 5 years ago. The other thing we're doing is committing to zero net emissions. So we were the first major company to commit to carbon neutrality in 2007, achieved 100% renewable energy in 2017, which is about 8 years ahead of our peers' commitments, the other cloud providers who've committed to do this by 2025. And then sustain that for all the last 4 years. We're in our 4th year of 100% renewable, and this is across all of Google, not just Google Cloud. The other thing we've done is gone back and essentially purchased enough renewable energy and high-quality carbon credits to go all the way back to 1998 and try and do our part to erase the carbon legacy of the company as a whole. And again, this is the entire company, office space and everything, not just our cloud operations. And then finally, we've got the most aggressive commitment to going fully carbon-free, and that's really hard, but we've set the stake in the ground of 2030. So just a quick view of the efficiency of the data centers. We're not going to be able to match the world's most efficient data center that, at NREL that Steve and team are doing, because they're really driving research, but we can drive efficiency in. And you can see since 2008 and 9 through the current period, we've gotten down to an average PUE of our data centers of 1.1, which I think is really good. I think Steve's data center, the latest I saw, was 1.036, which is phenomenal. But it's very hard to operate in all the regions, all the Google data centers around the world, and get an average of 1.1. So we're quite proud of that. In terms of how we got there, Google's been a leader in artificial intelligence, and one of the things we realized is we could turn AI to help solve this problem. So we used to have people who manually looked at all the sensors and wrote programs to do data center control, and we realized that if we just handed over the roughly 2,500 data streams that come in our data centers, and put the control, there were about 20 different controls in terms of pumps and temperatures, and just put that under the control of an AI system that we could actually do better. So I'd like to show you the results of that. Over the course of 1 year, when we deployed this into our data centers in the fall of 17, to the following August, this is July actually, we were able to actually have the AI model see the results and build on its training set in real time and continually refine itself. And we're able to reduce our cooling needs by 30% just by handing over our data centers to AI. So this is something now we deploy broadly. To the point Andrew made earlier, even if you want to commit to being carbon-free, the problem is there isn't carbon-free energy available all day. So our workload, the energy supply is very spiky. The sun is shining during the day, it gets windier at night, and if you just present a stable load, then of course you can't run carbon-free. So two things we've done about that. The first thing is we actually do purchase renewable energy to match our consumption. So even though we're not necessarily using that solar or other power during the day, we're buying the renewable energy so that it is getting purchased off the grid. Because one of the travesties, of course, is if we have wind farms and solar farms, they're generating power and nobody's buying it. So we purchase the renewable energy to match our consumption. And so even though in the evenings we have to run on coal-fired, like everybody does, at least the maximum amount of energy has been put into the grid, and that helps support the industry. The other thing we've done is we've actually moved away from this idea of just presenting a relatively constant load. And Andrew made this point about trying to really modulate the usage to match the energy supply. So in our data centers, we actually align with the availability of low carbon energy, and we compute more when the wind is blowing and when the sun is shining and when we know that renewable energy is actually being injected into the grid and we can use it. So we've been modulating our usage to actually align, and that helps lower the net carbon or the gross carbon footprint in addition to the net carbon footprint that's zero. So in order to extend this to our customers, there's a lot of folks in corporations and institutions around the world who have a commitment to sustainability. The challenge is, how do they get there? As Andrew said, you can't just go out and say, I'm going to buy from a renewable grid. It doesn't exist. So one thing that folks are doing is they're adopting cloud computing, knowing that the Google Cloud is a net zero carbon today through all the renewable, and is moving to gross zero by 2030. But to give people a better view into their carbon footprint of their computing, we've recently added to our dashboard essentially a carbon report. So you can actually see what your carbon footprint is gross. Of course, net is zero, but gross. You can see the carbon emission trends. You can actually align your own computing to do that same thing I was describing, which is do more computing when it's greener. So we're trying to give that visibility so that folks can actually align toward this goal of a net zero grid. So just to wrap up, first company to become carbon neutral, first major company to get to 100% renewable and in our 4th year, and working towards that goal of being 24/7 carbon free. I guess one last thing I'll say is that in 2018, I believe it was, maybe 2019, we made the largest corporate renewable purchase in history of about 1.6 gigawatts of solar that, as part of our portfolio, got us to 5.5 gigawatts of contracts for renewable. So those are places where we contract directly with energy providers to ensure that we're able to get that supply to run our data center. So it's a small step, but it's a step hopefully in the right direction. Thanks.
Thanks, Bill. Thanks, Bill. That's terrific. And I just wanted to say, one of the reasons that we invited a representative from Google to be a part of this panel is because Google deserves credit for being one of the leaders in pushing, a more sustainable computing agenda, not just for itself, but for the whole cloud and computing community. So that's wonderful. Of course, we all still have a long ways to go, right? But we're by no means done. Okay, so you wanted a quick, at the very end?
Yeah.
I can let me just, yeah, oh, okay. So let me just open it then. Well, it won't work with, I am sorry, but it won't work with
Zoom?
Yeah, Zoom won't share the app unless sorry, we just need to do one quick minute of logistics here. If I were more talented, I could introduce Michael at the same time I'm doing this, but I'm not quite that talented. I apologize. Okay. Why don't we let you go ahead, and then we'll get that up at the end. So our next speaker is Michael Mcnamara. And Michael is the CEO of, I think, one of the most exciting new computing meets power grid kind of companies. And when I first met him, now almost 3 years ago, I was astonished that he was able to ingest really the complexity of what's going on in power markets and renewable energy generation and power grid dynamics, and at the same time absorb a lot of the challenges around computing that we wrestle with every day. So he's going to tell us a little bit about what's going on at Lancium, which I think is, as I said, in my opinion, one of the most exciting companies out there in this space. Where does Zoom go? The endless challenge. It's not the Zoom window, the other Zoom window. Nope. I think maybe if I just click on
It seems like it's working.
it's working, right? You guys seeing the slides? Okay, I'm sorry. Michael.
Thank you, Andrew.
About that.
My background is energy, not computing. If you want to talk to computing, we have some of our folks here. So I'll talk about some energy trends that are very important. And that is the trend of the decarbonizing of the grid. There's a number of ways to decarbonize the grid. I think our view is the highly most likely, most cost-effective way is to add a tremendous amount of wind and solar and storage. And in fact, a feature of the decarbonized grid with the systems, you have to overbuild wind and solar. Because the way you resolve the intermittency of wind and solar is you build too much of it, which is a fundamental change in the power market. Another key element of the power market of the past was you would put the generation stations where the load was. And that if Dallas or New York City were growing, the utility would add a gas plant or a coal plant in the city environment. And that's not what we're doing anymore. We're very active in Texas. There's not a single coal plant that we built in Texas. I believe there's one gas plant that we built new in Texas. There's hundreds of new wind and solar. And what that results is something that was unseen in the power market really until just the last 5 years. And that's the incidences of negative priced energy. Very rarely you would see negative price energy next to nuclear plants at nighttime. Nuclear plants do not like to go up and down, so the nuclear operator would just absorb the cost in order not to stress their nuclear facilities. And you'll see here the trend from 2013 to 21 is negative price energy is now endemic. And it's endemic because the grid of the future has too much wind and solar. Storage is a solution, but storage generally only runs for about 4 hours. The way to solve this problem is to build at extremely large scale many data centers at critical points on the transmission system in every grid operator that is going decarbonized, which is all of them. I'll show you the example of Texas because it's ground zero, because it's a deregulated market. It has very ample wind and solar, but the trends you see here are happening everywhere in the world. I just saw that there's a plan in Chile to put 600 gigawatts of solar panels and run a high voltage line across the Pacific to Asia. They're doing the same thing in Australia. It'll feed Singapore. There's a group in England trying to do it to take wind and solar from Morocco. And I'm sure you're all familiar with the fiber lines that cross the sea. There may be a future where the ultra high voltage direct current lines do the same thing. But what that results is all the points of interconnect are often overwhelmed with too much wind and solar. And to the extent that you cannot find anything useful to do with that, you slow the growth of wind and solar because the economics cannot be underwritten. What you'll see there is negative priced energy occurs now 20% of the time in North and West Texas. And what's happening with the trends? They're only continuing because there's an increasing desire to buy more renewables. You buy the renewables where they're plentiful, and the infrastructure bill will only turbocharge these trends. This is the fuel mix in ERCOT, which we should all be very pleased with as a trend. You'll see that coal has gone from 37% of power generation to 19%, while wind has gone from 2 to 23. And if you poke up at the upper right-hand corner, you'll see solar's 2% of the grid today, and it's going to go much, much higher. So what is the solution we have in mind? The way you connect the renewables to the load centers is the transmission lines. It's very difficult, very time-consuming to upgrade those lines. One, who pays for them? Two, how do you permit them? Three, how long does it take to build them, get the easements, get the right-of-ways? What you'll see in white is something called the CREZ system. The CREZ system was designed and planned in the early 2000s to accommodate the growth of renewables in Texas. It was supposed to work for 30 years. It was swamped in about 3. And it's swamped today. And what's happening because of the trends we've talking about? More wind and solar come to North and West Texas. So our vision is data centers should act as enormous inverse power plants. And what power plants do is when the grid is in times of need, power plants go up. The grid is indifferent if a power plant goes up or a data center goes down. There's another thing we do which is very special. We're the first in the world to do it. In West and North Texas today, the grid is weak. It has no momentum. It has no inertia. Inertia is provided by spinning masses, thermal plants. Inverter-based resources, wind and solar, provide no mass. If you have a clever control system and control servers at very large scale, very fast, you can make servers act exactly like the governor on a generator. And it backfills the inertia that the fossil plants used to provide. So the vision is to build a data center running from, or a number of them, starting in Shamrock, Texas, going south through Abilene, and west all the way to El Paso on every single one of those lines. What happens? They consume negative priced energy. They provide the grid inertia that the grid needs because of the retirement of fossil plants. And the net effect, if you can run these in a highly flexible manner, is negative 8 million tons per year if you build 5,000 megawatts of data centers. And that's in Texas alone. And that's what we're doing.
Thanks, Michael, for that exciting view of how computing can actually be synergistic with the grid. I'm going to try and find Eric's slides here. So our next speaker is Eric Riddell, who is currently a Senior Vice President of Engineering at an exciting firm called IT Renew. But many of you may know him for his distinguished career as a researcher in storage systems and a number of other executive roles. He's going to tell you something, I think, about IT Renew today. Let's see, which is the IT Renew slide?
It's on the left.
There. Thank you. Eric?
Thank you, Andrew. Yes, it's probably all in my 10th supercomputing, one way or another, but I'm definitely not always a regular attendee. But I am responsible for building lots of computers over the course of my career and putting them out there to use the energy from various places. And so what I'm going to talk today about is the systems that we're building at IT Renew. So we build racks of servers like this, right? Supercomputing is one of the few places where you can still see racks of servers on a show floor. But we all know, as we've heard here, there's racks and racks of these servers all over the world, computing of various kinds, right? And so what we're trying to do is we're trying to reduce that carbon footprint in a way that is practical and available today. And so the way that we impact the carbon footprint is as shown here. So we focus on those scope 3 emissions that Andrew talked about and Steve mentioned at the beginning. So the reducing, extending the life of IT equipment and therefore avoiding new IT equipment being created. And so that's the 75% savings. So depending on how efficient your data center is during the use phase, what the PUE and so on is, the higher the percentage of carbon tied to pre-use energy is going to be. By using schemes like ours, we will save our customers up to 75% of the carbon by focusing on avoiding new motherboards, new chips, and so on being created by extending the life. And the good news, as Steve also mentioned in the beginning in his talk, is he thought that some of the technologies that they were using might come at a premium. Our technology doesn't come at a premium. In fact, it comes with cost savings. So 50% hard dollar savings in terms of the computing because of the way that we source the material. Right? So we're taking recertified equipment, we're extending the life from sometimes 2 and 3 years out to 4, 6, and 8 years, and therefore avoiding all that carbon, but also saving money for those customers directly. Right? So the customers save half the money, the world saves up to 75% of the carbon. And then finally, we have the operational savings, which we've already heard about, from more efficient and more effective ways of doing the system design, right? The core of what HPC and supercomputing is about, how to take the same algorithms, implement them more efficiently, so there's less demand on the computing, and then how do we take the hardware of the computing and waste less energy, whether we're wasting energy within a set of gates, moving electrons back and forth, whether we're reducing energy in the photons in fiber optics, or we're reducing the energy that's needed to do the cooling and so on, right? So the good news for our customers is that there is savings and efficiencies across the board, and this is a model that's available today. So our Sesame product line, which is those racks of servers that I said, we've been selling them for about 3 years. We have systems with some of the folks in the room here. But the parent company, IT Renew, has been in the IT industry for almost 20 years. And what the core business of the company does is decommissioning of data center equipment. So we work with all of the largest hyperscale companies out there, Microsoft, Google, Facebook, Uber, Dropbox, you see some of the logos. And our core business is responsible for decommissioning their data center equipment. So basically the core business is a rack be gone business for these hyperscale customers. When they're done with a rack, they say rack be gone, and we take care of all the details of what that means, right? And so what we found after a couple years of doing that, right? So one of our biggest challenges initially is there's end user data, customer data, right? So we have some disk scrubbing technology, we have big disk drive shredders, which as a former Seagate employee are really painful to my heart, and they also make a lot of noise. So it's really a dirty process, but that's what our customers demand. But then once we've removed the end user data, we end up with a bunch of material that we try to create economic value from. And so that's servers, CPUs, DIMMs, network chips, racks, power supplies, et cetera. And what we try to do is bring those back into the supply chain. And so what you see on the right-hand part of the chart, items 2, 3, 4, and 5, is repurposing of that IT equipment. And the top 2 highest value items is our Sesame solutions. So we create either racks of IT equipment, as I showed you in the previous slide, or edge solutions, which is basically for us code for any set of servers and motherboards and computing that's not in a rack form factor. Right? So we can create form factors for going into a closet or onto ships or into factory floors, et cetera. Lots of ways to reuse that same material that we're taking out of the data center and producing it, reusing it. Now the important thing, the reason that this works is the economies of scale that we have. So we'll process between 35,000 and 100,000 servers per month through 10 worldwide facilities. So in the course of the next 12 months, we'll process over 2 million servers. Last year was an up year for server builds, which means it was also an up year for decommissioning. And so we pull from that supply chain pool. So that means, in addition, in today's day and age, where some companies are having their customers wait for 3 months and 4 months and 6 months, we also have a time to market advantage because I have almost 1 million servers in my warehouse right now, and we can deliver them in 2 or 3 weeks, where some of the other computing companies out there are telling their customers they may need to wait 7 or 8 months, right? So the important thing for us, as I said on this slide, is there is no compromise, right? There's no compromise in performance, because that 50% is a performance normalized cost savings. And most importantly, there's no compromise on the carbon side, because every server that someone buys from us means that there's a motherboard that doesn't need to be manufactured fresh in Taiwan, and that reduces that carbon footprint. So we're glad to be part of this ecosystem today, and contribute in the ways that folks have already talked about here on the panel. Thanks.
Thanks, Eric. Terrific to hear about what's going on at IT Renew. So with that, we've completed sort of the presentations from the panelists. I'm going to put up a couple more questions, but please do think about questions you might be asking the panelists here in just a moment. So some of the questions, in addition, to try and provoke the audience here, beyond the challenges for sustainability in multiple dimensions, might be, what is our responsibility as a community, right, to do something about sustainability, in addition to, of course, the many other challenging missions we face? What are some of the most challenging obstacles, right, that you think, your organization might face in making forward progress in some of these areas, and, questions about the different solutions that have been proposed? And what kinds of goals should we have about trying to reduce or even eliminate our negative environmental impacts? And what do you see as exciting, game-changing maybe opportunities? So with that, we're going to open up the floor to questions. Actually, sir, if you could help us with the microphone here in the room. And I was just going to start us off by asking Eric a question. So you talked very much about the IT Renew system, right, in business for actually recycling this electronics, but obviously, even though we wish you great success, the computing industry is really large, right? And I heard about something called CEP or something like that. Can you talk a little bit about larger efforts to create circular kinds of ecosystems around computing equipment?
Absolutely, yeah. So we're just a part of the puzzle here. So there's a number of organizations that are really trying to raise the awareness, right? Because Bill alluded to this as well with carbon reports and so on. Is what we really find is once people start to think about what am I doing here? Where's my footprint? Why am I throwing away these servers? Why am I buying new servers every 3 years and so on? They realize that it's not always necessary, right? It doesn't fit the task, and a number of these are just habits, right? And in some cases, bad habits, right? And so that's what things like the CEP is organizations to increase that awareness kind of industry-wide, not just in data centers, but also in everyday computing.
Terrific. Maybe we'll bring Steve in quick for a question. Steve, if you're with us, you talked about that super exciting hydrogen fuel cell, right? Prototype data center system. What are the obstacles in preventing us from actually having those things as large-scale deployments in the near future?
It's the availability of hydrogen and the infrastructure to distribute it. As Michael noted, Texas Panhandle will be an ideal place to co-locate electrolyzers with all of the renewable energy that's there, take advantage of the negative energy pricing, produce low-cost sort of dollar a kilogram hydrogen that could then supplant the steam methane reforming and be available for fertilizer use, but also for data centers. He mentioned some of the challenges with getting power out of the Texas Panhandle and right of way for transmission, but maybe easier to move a pipeline rather than transmission lines to move hydrogen. But 5 of the world's 10 largest wind plants sit in the Texas Panhandle, and the more we rely on clean sources of energy, such as wind and solar, having constructive and beneficial uses of the energy that can take advantage of when it's produced efficiently, which may be out of cycle with our normal energy use, be that a data center or production of hydrogen or other sorts of transportation fuels for maritime and aviation. But the biggest challenge initially is the distribution of hydrogen and getting that to data centers or locating data centers where it's available. And then I confess there's a bit of a conceptual challenge, because I think the lingering image of the Hindenburg is something that's daunting to overcome.
Terrific. Thanks, Steve. Anyone in the room?
How's it going? Can you hear me? Awesome. We talked a lot about kind of wind, and in America, I think we think of wind, but we're kind of right now limited to onshore wind, right? With more and more, I guess, leases coming available on the East Coast for offshore developments, what potential opportunities do you see to couple that with the data center and high compute market? And I guess for offshore wind being what, 90% efficient compared to onshore, so some pretty significant opportunities there.
It's a good point. We think there's a large opportunity set. Of the offshore wind plants, there's one coming to New York City. It'll interconnect into Long Island or Manhattan. Simultaneously, they're building the wind and solar north of New York City, which there's not much north compared to Long Island and New York, which will mean there'll be a tremendous amount of congested energy, potentially as much as you'll see in Texas. Those are all opportunities for data centers. Another one of the larger offshore wind plants is interconnecting into Maryland. The only place they could land the line is in the middle of nowhere. The transmission system needs a massive upgrade. In the meantime, it's a perfect place to put a data center.
So if I could try and stir up a follow-on discussion for that, maybe between Bill and Michael. I mean, one of the challenges seems to be the traditional model we have of continuously on data centers, continuously available and so on, and the relative variability of renewable generation, right? What do you guys see as the challenges for bringing those two things together in the future?
Maybe I'll comment. I think the computing model that we're used to is really one of two things. One is on demand, right? I need to do some computing and I need to do it now. And for services, that's critical, right? You can't have someone visit a web page, for example, and have the page load 3 days later, or when there's more renewable energy available. The other model we all use in HPC is I'm willing to wait in line, but the goal is actually to achieve that steady consumption, because we're trying to drive up utilization. So I think there's room for new models here where people actually still take that batch approach, which is I want to get the work done and it doesn't have to start right away, but then couple that with these ideas like I was showing of how you can modulate consumption to align with the availability of the energy, and it kind of fits in the middle area there and can help us still get our work done and align to clean energy.
Thanks, Bill. There was someone else? Yeah. Over here, on the right. Yep.
Oh gosh, I guess I need to talk louder than I normally do. Okay, so one thing that I'm hearing a lot is that data centers are useful for eating up this excess power consumption. However, in the end, transmission lines need to be upgraded. How long can there be enough, is there enough demand for data centers to keep this up indefinitely until transmission lines happen? Or do you figure there's a breaking point where somewhere there'll be congested power and there'll not be enough demand for a data center to the point that it would actually be harmful to make one, and we just need to try and force the transmission problem? Like, is there an upper limit on how much you can use this technique? That comes to mind.
Michael, do you want to field that? I have an opinion, but please.
At least in West and North Texas, they'll build solar and wind until the state is full. Then it could grow 1,000-fold. So there is no theoretical limit on the amount of load you can put at those locations.
Well, I meant more a limit on how much you can apply the data center technique. Like, how much willingness is there to keep making data centers to eat this, or will there eventually need to be something else? Or does it just come down to pray that infrastructure makes new lines?
If the transition to hydrogen happens, the electrolyzer power demand will swamp data centers by a very large factor. And that's, I think, to our mind, the biggest potential next addressable market.
Yeah, so at some point it just has to be the infrastructure.
So I'm going to express maybe a slightly different perspective on it. So when we started studying excess renewable power, we were asking the very same question, right? Is this a transient phenomenon? When things come back into the balance, will this problem just go away? And what we were able to convince ourselves is that these imbalances come fundamentally from the fact that you have variable generation. It's a statistical process, and as long as you have that variability, there's going to be lots of places where it's uneconomic to build sufficient transmission actually to bridge it to the load. So you can convince yourself that as renewable energy grows as a fraction of the power grid generation, that necessarily the frequency of these excesses and the magnitude of the power available from these excesses will continue to grow. Now the wild card is how much of adaptive load or flexible load or storage or hydrolyzers, as Michael said, can eat that up. But it does appear as we go from a 15% to 25% to 50% to hopefully 75 or 90% renewable grids, that you're talking large multiples, right, in the magnitude of the statistical variation that are probably much larger than even what Bill's colleagues can grow at Google over the next 10 or 15 years. So if we're going to get there, right, and there's significant challenges, I think the variability of generation is just unbelievably large, right?
Okay, thank you.
Other questions?
Down here.
Hi, Brian Renner from Smith Group. I think the hydrogen discussion is really fascinating, and it comes down to the distribution. I attended a talk recently by a major generator manufacturer who was looking at ways to take the conventional standby generators that we're all used to seeing, both diesel and natural gas. I mean, the diesel, I believe they were talking about hydro-treated vegetable oil as an alternative to number 2 diesel. In fact, it can be used either or. And the ability to use hydrogen or a blend of hydrogen and natural gas in their line of generators. I'm wondering if anyone's had any exposure to that yet.
Steve, maybe? Did you want to speak to that? Yeah.
I haven't looked at that directly. We've looked at drop-in replacement of fuel cell-based sort of backup generator. It could be done sort of in a shipping container where you have sort of the configuration we looked at was roughly a half a megawatt generator, hydrogen fuel cell, and it was driven by bottled hydrogen. So you get around the infrastructure by simply relying on the current distribution model, which is of delivering bottles of hydrogen. There are a few advantages in the short term that you use the backup generator, your diesel generator. It's for emergencies only, and you're governed by noise and emissions. So you can use it in emergency, but you can't use it for load shedding. So one of the attractive opportunities that we wanted to explore, I have to confess we have not yet done that, is if we had a hydrogen fuel cell as our backup generator, we could operate it when we wanted to, because they're silent, they're very responsive, and we're not governed by the same operating restrictions as if we were running a diesel backup generator. And then we could look at opportunities for load shedding, and in cooperation with our utility provider, we did some analysis to cost effectiveness of that for shedding load in times of high demand, or we have peak demand pricing, so we would use that to reduce our own demand, to reduce peak load charges that we incur through our utility. but I don't know what opportunities we would have in any of those areas if we used other, blended fuels or something other than hydrogen, because I just don't know the particulate and the emissions associated with, vegetable oils or blended hydrogen and methane.
Terrific. Could I get the operator to put us to galley view or something like that, so when Steve talks, we can see him? So I was going to ask each of the panelists the following question. So we've heard from a bunch of panelists that, it's not so clear that it's an economic obstacle, right? That sometimes being more sustainable can actually be a financial win, right? So that's great news, right? And maybe that's true in some cases. Maybe that's understood amongst the panelists. Maybe it's not understood by everyone in the community. But I'm curious if we could just ask each of the panelists to speak to the question of what do you run up against, right, when you talk to folks about trying to adopt some of these new ways of doing computing, either internal to your organization, maybe in the context of Bill, or folks you're selling to, right, in some of these other settings. What are the gotchas or the showstoppers that are the challenge? I can tell you one of the things I always hear when I talk to other cloud partners is, that this drive for 5 nines and capital efficiency are what people view as the big challenges in enabling, for example, more load shifting. So I don't know who wants to go first, but it'd be great to hear what you guys see as some of the challenges.
I'm happy to jump in, Andrew. I don't know.
Please go ahead.
Hear me? Yeah, the biggest challenges are not technical, but it's alignment of the benefits, right? And I happened, in my prior role, I had the benefit of playing benevolent dictator, right? I had a heavy hand in the data center design, driving the efficiency, the choice of vendor for the system, but that's not always the case in organizations, right? So here I from an IT perspective, if there's a little difference between systems, but one provides, I'll just say one's air cooled and one's liquid cooled, right? Then I got to work with the facilities folks to make sure that they have the investments in liquid cooling, for example. But the savings go to finance, right? So making sure that everybody benefits is probably the biggest impediment, because I may have to make a choice between 2 different computer vendors. Facilities has to make some investments. They've got to take some of their resources and do things differently, right? And some of these are generational changes, right? You get somebody who their entire life is used to making data centers feel like meat lockers. But at the end of the day, when there's financial incentives, unless there's something, my budget was responsible for the utility costs of the data center, right? So if you got to take all of those things into account and make sure that everybody who contributes a little bit to making it effective also realizes the benefit. And that's, so you've got to get your IT folks, the folks who are the users and finance all together in the same room, all pulling in the same direction to make sure that everybody benefits. That's been the biggest sort of observation about why some of these changes are slow.
Thanks, Steve. Gentlemen?
Yeah, and Andrew, I would echo that. It's the silos between different teams and different groups. When we talk to an enterprise customer where the networking team is still different than the storage team, is different than the compute team, because they didn't read the memos about cloud, right? And so I know that their data centers will have low utilization, right? And that's the first step of cloud, right? Get your utilization from 10% to 35, maybe 40% aspirational, right? Very few folks, other than probably the largest public clouds, are at 70, 80% utilization. And those silos remain, and so our most effective customer, our most effective advocate is the person who has the magical spreadsheet that just includes everything, right? Includes the facilities costs and the personnel costs and the power costs and so on. And then it's just glaringly obvious right there on Excel on the screen, that there are more cost-effective solutions available, and then oftentimes that can be the go-forward choice, right? But those silos absolutely still persist across the industry.
Yeah, I'll just make a couple comments here. One of the big challenges that our customers bring to us is they have a mandate and or a desire to lower their footprint. They're very aware of that. The desire is almost always there. A lot of folks just don't know how to get there. And if you can't find a path to get there at an organizational level, if there's any one big piece that you don't know how to solve, then it can stall the whole process. So one of the things they're finding attractive is if, there's two paths, right? One is if you're operating your own data centers, figuring out how to track the state of the art and really drive your PUEs down, right, and go source energy and your renewable contracts. And it's really quite a load on an organization, just as scientists oftentimes don't want to become IT or HPC facilities experts. Facilities people, it's very difficult to track the latest in the industry. So sometimes what we're finding is folks like that they can just move their operations to a cloud, and with that, get that piece done, and then they can go work on other parts of sustainability in the organization. The second thing, I talked a lot about gross carbon and net carbon. We're operating net carbon neutral because of the renewable, but organizations now we're moderating our own usage to align with renewable availability and wanted that insight. So things like I showed you with this dashboard and visibility, and I didn't talk about this, but AI-based systems that actually make active recommendations. You can reduce your carbon footprint by moving from this machine type to a cheaper one, because that cheaper one is also a slice of a machine. So we can monitor, we don't see what people are doing in our cloud because of privacy, but we can see utilization levels and make active recommendations to lower their footprint, and customers do appreciate that.
I've been to the NREL machine room. It's beautiful.
Me too, I love it.
Our data centers are not like that. We have the world's lowest cost, lowest end data centers. They have no liquid cooling, they have no HVAC, they just move a ton of air. And we've been running tests for years. We've been running hot aisle temps 110 degrees Fahrenheit, and have had very limited server failures. We also ramp the servers very often, very drastically. This is something that traditional customers are not accustomed to and are not comfortable with. So we own the servers. We end up buying second or third generation servers. Since we have no power constraint and no real estate constraint, we just throw more nodes at a problem. And if you can deliver that whole system at a very low cost, it's effective. But it's a different way about thinking about a machine room than is normal.
Yeah, and there really is still a wide dynamic range, right? So I spent almost 10 years at EMC positioning clouds to enterprise customers, and the dynamic range of data center efficiency and data center consideration for energy consumption for any of it, easily 2 orders of magnitude, right? And the interesting thing was that a lot of those folks who were in the middle, they thought they were doing a really great job because they were better than these guys, right? But we also went into the Facebook and the Google data centers, and we know how you could really do it. And that's just an information issue, right? That's not about changing your business model, et cetera. It's about breaking down some of those silos, educating, and then there's a huge dynamic range that we can still get to this end of efficiency.
Maybe one more comment about dynamic range. One of the challenges we face in high performance computing is the computing we're doing, there's value to those computations, whether it's scientific discovery or time to market to get a more fuel efficient car design before the model year. We can't necessarily move to the older generation systems, and that's why we refresh aggressively. One of the nice things about the cloud ecosystem, and also the way this hardware is retired, as you heard, and is reused, is there's this dynamic range of workloads. And when you have a very large installation, such as a cloud, but and this whole I don't know what the right word is, spectrum of options, you can do workload placement that changes over the life. And so essentially, you can think almost like a pipeline where high performance computing is coming in and demanding the most performant infrastructure each year. And there's always workloads that don't need that same performance and can fill and extend the life of the machines. And then ultimately, when they do need to be retired for whatever reason, they can take on a second or a third life. as we're hearing. So that's really attractive. And in the commercial space, and for the academic space isn't as much as an issue, oftentimes the constraint is not the computing power or cost or data center or personnel, it's the license cost. And the cost to run is really tied to the performance of the cores. So the TCO of the HPC calculation is really tied to staying on that latest, greatest hardware. So commercial customers in particular struggle with this issue of having to have very short lifetimes and turning around and creating e-waste. So this again, this ability to aggregate resources and have this whole life cycle for the machines and life cycle for the workloads can be quite helpful.
Terrific. So I wanted to call out and highlight a couple of things that were said actually, because I think that maybe translating a little bit to some of the government run and government funded kinds of activities. So it's some of the challenges I heard were siloing, right? People responsible for different functions, or maybe financial siloing, where there's different grants or different programs that pay, say, for capital equipment versus operational cost. We have examples, at least I can speak for the U.S. Funding of some supercomputers where the two are not really related. So that makes it very difficult to do any kind of integrated TCO optimization that might trade one for the other, or might trade lifetime for capital or what have you. So I think those are some of the challenges we have to get through if we're going to get to making more rational global kinds of decisions for some of these things. We've got a couple more minutes left. Any other questions that the audience wanted to raise here? In back. Yep. Oh, yeah. You can do this when you speak if it helps.
Okay, thanks. Matan Erez, UT Austin. I'm just wondering what the, you talked about sustainability in terms of carbon neutral and things of that sort. Is there a cost to the carbon offsets versus just savings? Is one preferable to the other, or are they really identical? I'm just curious. I don't know the answer. And I have a second question, but maybe I'll let you answer the first one, and I'll hold on to this.
Yeah, there's definitely a difference between carbon offsets and there's even notions of high quality and low quality carbon offsets and renewable. So when you're buying renewable energy, you're actually ensuring that energy that's being produced is going into the grid.
Sorry, I was actually thinking of the other, level 3 or whatever those were called. The investment in the center itself.
So maybe one thing that would be helpful to say is that there's two terms that are widely used. One is carbon neutral, which you can get to by purchasing various kinds of offsets and so on. And then there's another goal which a number of organizations have adopted called net zero, right? Which is an attempt to actually minimize sort of the total carbon emissions that sort of ever happen as a result of your activities. And most people consider net zero to be much more difficult, but also a better goal, right, for the climate, if that helps. Yeah,
yeah, thank you. I had another question. You talked about sort of net zero and things of that sort. If you can get to it, of course, and there are no problems anymore. But if you cannot, is there a notion of sort of amount of useful work done per emission or per carbon unit or something of this sort? Because I don't recall this being discussed.
I talked a little bit about the amount of compute capability presented per watt.
Yes.
But the challenge is that every workload, as you know, some science codes are running very high peak efficiency and some are very inefficient algorithms. So I don't know that it's easy to define a unit of work that would be meaningful. I don't know if others have points of view on that.
One thing that I would add to that is it actually turns out that it's very hard to do that because it's not just, say, the quantity of power you consume for a particular computation. It depends on where and when you consume it. So it's very, very difficult to create a simple relationship between those things.
Well, it's something to optimize then.
Yes.
That's right. Yeah, and I think that's important. Is that it's across the spectrum, right? So I was at an event 2 weeks ago with some of the Linux community, and there's a Green Software Foundation that's focused only on making the software itself more efficient, right? That the libraries that are used in millions of codes all over the place, if someone just spends spends a little bit of time getting a 10% improvement or or a 2% improvement in some library that can reduce a huge carbon footprint, right? And we're now at the point where we can map that information, right? Whether we turn the AI loose on it, as Bill suggested, or we do it ourselves. But that just thinking about the whole end-to-end problem, it's massively multidisciplinary, and we should be able to do it now. We're there.
Actually, that's a great, Eric brings up a great point. So one of the big sources of e-waste, right, in the broader computing community is actually software forced upgrades or software increased demand for either memory or computing capacity or what have you. So one of the areas, if there were a way to actually, and this is a very difficult thing for this community because we always want bigger, faster, and what have you, if there were a way to actually trade increased investment in algorithms and software tuning and the like for reduction of actual consumption, that's another dimension, right, of e-waste avoidance or something like that. Back to the question of correspondence of work with say, carbon footprint, the relationship is so complicated that there are actually a number of companies that have already sprung up that are serving sort of dynamic carbon emissions data and so on. For example, my group has a small academic project trying to serve dynamic emissions data for research purpose, right, and so on, because it's such a complex dynamic process that is not even stationary, right? I mean, in the sense that it's changing rapidly as the grid changes, as demand changes, as demand grows and shrinks, and new transmission gets built and the like. So if we have time maybe for one more question, if there's one more question in the room. If not, I'm going to show one slide. So first, let me thank the panelists, right, for making the time to come, and all of the attendees for sharing their time here to learn about sustainability. Don't forget to fill out the survey for the panel, right, to talk about what you got out of this. But I just wanted to leave with a couple of thoughts. The first is that, while we sometimes think either we as individuals, can't make a difference, or maybe HPC is not the biggest part of computing, but I think we know actually, and people have demonstrated that no one community or person is actually too small to make a difference in this big challenge. And if we're going to be successful in reducing sort of the negative environmental impacts, that we probably all need to contribute. So let's engage in collaboration. Let's not engage in pushing. I don't think anyone in this room was blame shifting, but there is often responsibility shifting that goes on when we have these discussions. But let's work together and try and increase the sustainability of HPC and computing generally. Thank you very much for coming.
Thank you, Andrew. Thank you.
Thanks, Steve, if you can hear us.
Again, thank you, Andrew. Enjoy SC, I'm jealous.